Okay, hi everyone. I'm very excited to see all of you, or at least virtually. My name is Yoav Lehan. I'm a researcher at the University of Haifa in Israel, and I study different biophysical interactions in the ocean and in the atmosphere as well. I'm very excited of being here in this first virtual summer school of SOLAS. Actually, as a student, I participated in the first summer school a few years ago, and it's great every time being here is really nice. So I think you all know a little bit about SOLAS now, and the idea of the summer school is to increase your to make everyone know each other and know of SOLAS and of the other students or people that are involved in SOLAS. It's challenging. All these virtual school and virtual events are always challenging, and of course, there are disadvantages with respect to the actual meeting. But still, I think we can all benefit from it and from exchanging ideas and knowledge and knowing each other and learning from each other. The first, before we start, I would like to introduce Krista, who is who have led the summer school, the preparation for the summer school, and who has done, I allow to say, tremendous work doing it. And I'd like her to say some words for introduction.
So then thank you, Yoav, and welcome to all. And I have to say, it was the whole organizing committee that did a lot of tremendous work. So thanks to everyone. So finally, we're here. So I'm glad that we could finalize this and everyone could show up today. I welcome you. And I would encourage you all, please, to put on your video if you can, because I really hope that we can still network and meet each other and interact, even though we have to do it in this virtual world. And with that being said, I hope that you all engage really in the summer school. We tried to make it as interactive as possible. So please discuss in the discussions, ask questions to the lecturers, use the Huba platform as much as possible. Ask questions later to all the practical leaders, to all the organizers, to the lecturers, as much as you want, please do, and to each other. And just for your information, Mindfully Wired is doing an excellent job at supporting us. And if you have any technical issues, they're there behind the scenes to help you. So please remember that they're there and you can always ask them in the chat or in Huba for help. Yeah, and I guess I just want to say, yeah, enjoy and have a nice summer school. And with that, I would give it back to Yoav.
Yes, thanks, Krista. And so, of course, as you know, the idea is ideally we would have this school in person, and I hope to see you all when we're all over the COVID thing and we have the actual non-virtual school, to see you all there and have even better an even better experience. I think Krista said everything concerning. So we have Paul and Becky from Mindfully Wired Communications to help us with any technical issues. Feel free to ask them, to address them with any issue you have. Feel free, this is a general comment, feel free, I allow myself to say on behalf of everyone, feel free to address everyone, lecturers, other students. The idea is to interact. So the more interactions you have, you will benefit from it and we will benefit from it. So this is the overall idea. The sessions are recorded and they will be uploaded to the Hoover platform at a later stage. So with no further ado, I think so today we can start with the actual session or with the day. And today we will focus on greenhouse gases, obviously mostly on the oceanic regime. And we will first have a plenary session, then we will have a practical work, and then we will have a rapid posters presentation. And I think we can start, right? Unless I'm missing something, I think we can start with the plenary session, and we will start with Pinho. Who will talk about greenhouse gases in the ocean. So the stage is yours.
Hi, good morning to everyone. I hope that you can hear me. I have some problems today, and I am talking with you by my mobile phone, so I hope that everything works well. And first, I would like to thank the SOLAS 2022 organization to invite me to speak here today. And I apologize if my English is a little bit hurting, but I haven't used this too much in the last few pandemic years. And so I hope that I can communicate well with you. And my name is Luana. I am a professor at the Faculty of Oceanography and the University of Rio de Janeiro State, Brazil. And I will talk about greenhouse gases and the oceans. That is the theme of the first talk, the first session. And today is the first lecture of the first day of the event. So I thought that it will be more appropriate to start the day, remember some general concepts on this topic. So if it's a little bit obvious for some of you, but sometimes it's important to remember some concepts. So for start, what are greenhouses? They are gaseous substances naturally present in the atmosphere and that absorb part of the infrared radiation emitted by the sun and reflected by the Earth's surface, make it difficult to this radiation, the heat, to escape into the space. So these gases act like a blanket, trapping this heat close to the Earth's surface. In sunlight is solar radiation, mostly the form of visible and smaller part of the ultraviolet energy. And this is also called shortwave radiation. And the clouds in the Earth's surface reflect some of this incoming solar radiation back out to the space, and approximately 30%. And some part of this absorbed by the atmosphere, and the remaining half is absorbed from the Earth's surface. And the sunlight absorbed by Earth's surface acts to warm the surface. And this process is natural, and it's maintained favorable the life conditions in the Earth for microbials, for animals, for plants and inhabitants. And the global average temperature is 14 degrees Celsius. It's about 57 Fahrenheit, and which is approximately 33 degrees Celsius, warmer than temperature would be without an atmosphere and greenhouse gases. Due to their ability to absorb this infrared radiation, greenhouse gases molecules have a significant impact on the Earth climate and acting as barrier for escaping this heat. And who are they? At the composition of the atmosphere, we have many different gases. And the measure of the Earth atmosphere is composed of a mixture of only three main gases: nitrogen, oxygen, and argon. And the combination of these three gases comprise more than 99.9% of the atmosphere, of all the gas molecules in the atmosphere. These gases, which are most abundant within the atmosphere, exhibit almost no effect on warming the Earth. However, there are minor gases which comprise only a small portion of the atmosphere that do absorb infrared radiation. And these gases contribute substantially to warm the Earth's surface and atmosphere due to the ability to contain the infrared radiation emitted by the Earth. Yeah, like this blanket that I said before. Since these gases influence the Earth in a manner somewhat similar to greenhouse, and they are referred to as greenhouse gases. And they are only carbon dioxide, methane, and nitrous oxide gases. No, we have water vapor too, that I am not discussing here, but is the most part of these greenhouse gases. And we have two hydrochlorofluorocarbons, perfluorocarbons, and two hexafluorine, other small gases that works like greenhouse gases. But the first three are the most known and the most studied due to the concentration in the atmosphere and the special anthropogenic contribution. According to NOAA, the CO2 concentration nowadays was 4 to 0.99 parts per million in the last month, in May of this year. Methane was 1908.5 parts per billion at February, and N2O was 335.3 parts per trillion. So important to note this difference, no? Because CO2 is for million, billion, and trillion. So the concentration is a little bit different. And in the other compounds together, at up to only 3% of the total of greenhouse gases. Only, for example, to compare, the concentration of the SF6 was 10.88 parts per trillion at February. So it's much less than the other three more important greenhouse gases. And you say me, okay, Luana, you already remind me who are the greenhouse gas and their concentration in the atmosphere, but why should I study about the greenhouse gases in the ocean? And I say, because everything that happens in the atmosphere is related to the ocean. You will see tomorrow the session about air-sea interface and flux of mass and energy. And at Wednesday, the section about atmospheric deposition and ocean biogeochemistry. Thursday, about interconnections between marine ecosystems, aerosol, and clouds. And Friday, about ocean biogeochemical control on atmospheric chemistry. And in the fact, all the chemical, physical, and biological process, biological of the oceans is interconnected with the climate variation, and warm global. So it's too important to understand the process where these gases are and how they work in these different compartments. And in order to understand the change in the systems, and also to try predict change in the biogeochemical process, we need to understand the behavior of this gas in different ecosystems, including the oceans. So here we have the principal greenhouse gases and the main source, both natural and anthropogenic. And the first one in quantitative concentration, we have carbon dioxide that is produced when organic carbon compound like wood or fossilized organic matter like coal, oil, or natural gases is burned in the presence of oxygen. So carbon dioxide is removed from the atmosphere by carbon dioxide sinks, such as absorption by seawater and photosynthesis, by the ocean drilling plankton and land plants, including forest and grassland. However, seawater is a source of CO2 to atmosphere, along with land plants, animal, and soils, when CO2 is releasing during the respiration. And the methane that is the second most important in concentration. Methane is combustible, and it's the main constituent of the natural gas, a fossil fuel. Methane is released when organic matter decomposes in low oxygen environments. And natural sources include wetlands, swamps, marshes, termites, and oceans too. And other sources include the mining of fossil fuel and transportation of natural gases, digestive process in ruminant animals such cattle, and rice paddies, and burial waste in landfills. The third one, the nitrogen oxide, is natural produced in the oceans and rainforest. Man-made source of nitrogen oxides include the use of fertilizants in the agriculture, and nylon and nitric acid production, car with catalytic converters, and a burning of organic matter. And the other fluorocarbons gases are human-made and used to electric power industry in CFC substituents and other kinds of industries like aluminum production and semiconductor manufacturing. And all these gases are dispersed in the atmosphere after being emitted. For over a century, scientists have realized that concentration of atmospheric gases may significantly affect the Earth climate through this process. So, what interferes with the flux between greenhouse gases in the atmosphere? Because they are in the atmosphere, they was emitted or produced by different ecosystems, and they are in the atmosphere. And what is important, what interferes in this process? So both gases that are in the atmosphere and the gases that are in the surface layers of the ocean have the ability to exchange at this contact interface. And the direction and speed of these exchanges are related to several factors, such as wind stress, turbulence, water mixing, and many other things that you will see in details in the talks for tomorrow. And why should I study about this gas in the ocean? And what happened in the surface layer also affect the deep waters too. Once this water mass sinks, the concentration of gases that were in the equilibrium with the surface layer are carried to the deep regions of the ocean. And this is related not only to maintenance of the deep marine life, but also to the ability to retain gases for the centuries in these water masses. Once sunk, these water masses take hundreds of years to return to the surface. And here we can see the main surface and deep sea currents in the regions where they generally sink in the north part of this market in the map. And once this water mass sinks, they carry with them all the solid gases in equilibrium at the surface water. And that water will take hundreds of years to get back in the contact with surface again. So it's important to know the concentration, to know the process, and to predict what will happen in the next years and the next decades. But all the greenhouse gases are in the ocean, were originated from the atmosphere only. And no, as mentioned before, they can produce it within the ocean itself. Here we can see the scheme of carbon cycle in marine environment. I won't enter in details now, but it's just to show that they can be produced by biochemical process and released into the water column. CO2 levels and fluctuate gradually between the ocean and the atmosphere. So in the graph, we can see the yellow marks that represent the interchange of CO2 with atmosphere. And much longer cycles also occur on the scale of geological times due to the deposition of the weathering of carbonate and silicate rocks, and the deposition of the animals and the skeletons that can deposit in the sediment of oceans. And carbonate rocks like limestone are formed from the shells of the marine organisms buried on the ocean floor, and they are chemical eroded by reaction with CO2 in the air and soils when they are measured. And the ocean continues exchange CO2 with the atmosphere due to a large surface area and of the oceans and the high solubility of the carbon dioxide in the water. The ocean stores a very large amount of carbon, about 50 times more than in the atmosphere or the terrestrial biosphere. And each year, some of the carbon is released to the atmosphere, and a similar amount is taken back up into the oceans. And in addition, organisms within the marine biosphere photosynthesize and respire CO2. And due to their slow rate of mixing between surface and deep waters, only the surface waters are responsible for the short-term change of the atmospheric CO2. And as the atmospheric CO2 concentration increases, the ocean sink also increases slightly. And the ocean will eventually absorb the majority of the CO2 release for human activities, but this will take off 1,000 of years. So here it's only to show, we can see a smaller amount of methane are emitted by the oceans. It's another example. They are emitted in relatively small amounts from geological sources, such as steep methane hydrates, mud volcanoes, and geothermal systems. But one problem is the possibility of the future increase of methane emission, because a climate feedback process that is important to understand too. Large stores of carbon are thought to be present in frozen soils and permafrost of Arctic, and can increase the composition of this carbon as the climate warms, and may become large source of atmospheric methane and CO2 gases too. So it's really important to control and to monitoring the methane emission, because the feedback process could be worse than the smaller parts that are emitted directly from the oceans. Here's another example from hydrothermal fonts and hydrates of methane. So it's examples that we have produced inside the oceans about the methane gases. Here we can see, like the carbon, nitrogen also has a marine cycle that involves several biochemical processes, including to the production of N2O that can be released into the water column and exchanged to the atmosphere too. And this process can occur both in oxygenated layers and in low concentration of oxygen layers, and can be originated from nitrification and denitrification process. So today we will see too about the nitrogen process. So I would like only to show you that the NO2 can be produced inside the ocean too. And now we will start about talking about what are the implications for the planet of increasing the greenhouse gases in the atmosphere. As we have a red note here in this graph, we can see here in the graph that the greenhouse gases act as a natural blanket of the planet. So we have this figure that show the Earth with many blankets, and this capacity can help it sustain the life at the Earth. Sorry. However, what happens if this increase? If we put too much layers of blankets in the Earth? And what happened that since the beginning of Industrial Revolution, starting in 1850, humans have been burning these fossil fuels and release the carbon from the back into the atmosphere as CO2. Sorry. And process that took millions of years to remove carbon from the biosphere have been reversed. That's the same carbon is being released at unprecedented rates as a result of human activities. And atmospheric CO2 levels have increased 38% since pre-industrial times and are rising higher than at any time in the past 800,000 of years. So we can see the graph with the simulated natural factors only in the blue lines, and in purple lines, the simulated human and natural factors. In the green lines, the observed concentrations between this period of the time. And our forecasts indicate very worse scenarios if there is not a dramatic reduction in the greenhouse gas emissions to the atmosphere. Among the main problems is the melting of glaciers in the Arctic, which is directly linked with the increase in the water levels in the oceans. Not only due to the direct increase, but in the amount of water, but also due to the thermal expansion with increasing temperature. Here in this graph, we can see the different contributions and the direct rise of the water and the thermal expansion. So in the, I couldn't see it, but the yellow one, the first graph, I think it's the thermal expansion. The blue one is the added water, and the purple one is both conditions together. So the rising it's more that only the aggregates the amount of water.
Luana?
Yes.
Yeah, it's a bit complicated, the communication via Zoom. We need to start wrapping up, okay, because we're a bit behind schedule. So if you can start wrapping up.
It's more concise. I will finish. How much time I have? Or I finish my time?
It's a bit of time. We have some time, but try.
I will. Okay. Sorry, because I
just
can
know
see.
that we're a bit behind schedule.
Yeah. Okay. Because I can see in the mobile phone, it's difficult to see all things together. Sorry.
Okay.
This one, and the second graph, we can see the different pathways for future and sea level until 2 meters, if in the high, the worst possibility. The next one. Here we see the observation impacts and predict increase again in a scenario of drastic changes in the sea level, which are already causing change in the global sea level and impact several coastal regions around the world. Here we can observe the observed rising, the high rising at sea level. And the second graph is the prediction for the same regions with the worst scenarios. The other problem that the greenhouse gases are doing about the coral bleachings. Here we can observe the bleach of coral due to the impact on the microbiota associated with them, and how coral serve a production and feeding and reproduction for many animals. The loss of this ecosystem represents a major risk for the health of the ocean. So it's another problem that we have with the warmer condition in the oceans. Increasing in the concentration of atmospheric gases also have also been reflected in the concentration of gases present in the ocean. And here we can see the anthropogenic CO2 map dissolved at the water, and especially near the water formation in the north of Atlantic, and corroboration the impact of the atmospheric anthropogenic CO2 on increasing CO2 concentration in the water. And the other important problem that is associated with the CO2 or greenhouse gas in the atmosphere is that the atmospheric CO2 dissolved in the water form carbonic acids, and they are profound implication on marine ecosystem, due to increase acidity and causing acidification in the ocean. And the IPCC predicts different scenarios for the impact for the pH of the oceans. And according to concentration of CO2, they can contribute to release it into the atmosphere. So it can range between 8.1 and 7.8, the pH in the first graph. And this variation directly affects the balance of the carbonate system. And consequently, the process related to the carbon uptake by organisms, the consumption of carbonate ions prevents the calcification process of organisms and directly affect the growth and the reproduction of several species. And this impact also causes several damages to the balance of marine ecology, marine ecosystems. And in addition, the altering the carbonate balance, all this process can compromise the ocean ability to remove CO2 from the atmosphere, and consequently works as a feedback factor to greater CO2 emission from the ocean. And if their sinks capacity could be affected. So I hope I have managed to give you enough reasons to believe that it's important to study greenhouse gases in the ocean. And I am sure that probably during this week, you will have great talks going deeper into each of these topics that we start here. And I wish you all have a great day today. And thank you very much for the audience.
Hi, everyone. Thank you very much for this overview. As I said at the beginning, we will have all the questions. We'll have a session of questions and answers at the end of this plenary session. So I'm very happy to introduce our next speaker, Sarah Fawcett from the University of Cape Town. Will talk about warming up, turning sour, and losing breath, drivers of hypoxia in the southern Benguela upwelling system with implication to N2O prediction and fluxes. So Sarah, the stage is yours. Thank you.
Great, thank you so much. Well, yes, thank you for the invitation. Welcome, everyone. I'm very happy to have the opportunity to give this lecture. So this is now a very different format from the previous lecture, which gave you an introduction to the topic. Here, I'm actually going to talk very narrowly on some research that's ongoing in my group at the University of Cape Town, but that's relevant to the topic. And I will say that some of it is very new, so I hope you'll be with me, but I thought that it would be an exciting platform to talk about some of it. So yes, I chose to use this title, Warming Up, Turning Sour, Losing Breath. This was very famously the title of a paper by Nikki Gruber, which was talking about the sort of the trifecta of challenges to the ocean on the back of anthropogenic climate change. So warming up is obvious, right? Sea surface temperatures are rising. Turning sour is the ocean is acidifying, and losing breath is we now know that much of the global ocean is losing oxygen, and that the implications of this for a variety of different processes are dramatic in some cases and significant in all cases. And so I'm going to talk mostly about N2O today, so the greenhouse gas N2O, which you were very nicely introduced to. But in order to do that in the system that I'm going to focus on, I need to actually talk quite a lot about the ocean losing breath, or at least the idea of deoxygenation. But before I start, I just want to highlight that the work that I'm going to present is the combined contribution of a lot of different people's efforts, and I've listed the main contributors here on this slide. So this is most definitely not me alone. All right, so just because we're a diverse group of people, today I'm going to focus on the southern Benguela upwelling system. So this is part of the broader Benguela upwelling system, one of the global ocean's 4 major eastern boundary upwelling systems. And for those of you who are not in the southern hemisphere, this is actually an animation, it should be moving, but it doesn't really matter. In the southern hemisphere, you get southerly or southeasterly winds blowing parallel to the coast. And as a result of the Coriolis effect, this promotes the offshore, so to the left of the wind, transport of the Ekman layer. So offshore transport of water, which is replaced by newly upwelled, cold, nutrient-rich deep waters, right? This is the process of coastal upwelling. And here is a representation of those 4 major eastern boundary upwelling systems. So the Peruvian, Californian, Northwest African, sometimes called Mauritanian, and also the Benguela upwelling systems from left to right. And the top panels show you sea surface temperature, and the bottom panels chlorophyll as determined from satellite measurements. And the thing to take away from this is just, I mean, I assume some of you will be familiar with these eastern boundary upwelling systems, but if you're not, these are regions where cold nutrient-rich water comes to the surface. So for example, in the Benguela, you can see the colder temperatures right along the coast, and these tend to be associated, or they are associated with high primary productivity. I'm using chlorophyll here as a proxy for productivity. And the reason for this is that upwelling provides nutrients. So these eastern boundary upwelling systems account for maybe 1 to 2% of global ocean surface area, but they've been estimated to support up to 1/4 of the world's marine fish catch. So that makes them disproportionately important in terms of the implications for ocean productivity as well as socioeconomically. Okay, so today I'm going to focus on not just the Benguela, but the southern Benguela. So what you're looking at on the right-hand side is a map of the Benguela upwelling system, and it's divided into 2 subsystems, the southern Benguela and the northern Benguela. The southern Benguela is off the coast of South Africa. It's what I've put this blue box around over here. The 2 systems are divided by something called the Luderitz upwelling cell, which is this permanent upwelling cell that is so strong that it basically keeps the 2 subsystems completely divided from one another. And that's why I've made a bit of a point of saying I'm going to talk about the southern Benguela, because both hydrographically and biogeochemically, the 2 subsystems, the northern and the southern, do not behave in the same way at all. Okay. So the southern Benguela is an economically important region for South Africa. It supports a huge proportion of our commercial fisheries. The continental shelf in this region is fairly wide and shallow. This will become relevant later on. And upwelling in this region does not happen all the time. So for a start, there's a seasonal cycle. Okay, so upwelling appropriate winds blow in the summertime. And so you get really active upwelling in summer, and this relaxes in the wintertime, although we don't actually get downwelling. But even in the summertime, upwelling is pulsed, which means the wind blows for a few days, you get upwelling in response, and the wind drops off, and you get sort of a period of relaxation where productivity happens, and then the wind blows again. Okay, so this pulsed upwelling will become quite important. So it's not sort of a permanent state of upwelling and response. And then importantly for this talk, this region of the ocean experiences frequent events of hypoxia. So what do I mean by hypoxia? The oxygen concentrations, particularly over the shelf, so in the bottom waters over the shelf, which are about 200 to 300 meters deep, so much oxygen gets depleted from these waters that many organisms can no longer exist in them. Now, this is not to say that they completely lose all the oxygen. That would be anoxia. That doesn't happen very often in the southern Benguela. It's hypoxia. The oxygen gets so low, but the implications are vast. So what you're looking at here is a huge pile of lobster that died as a result of oxygen starvation in the southern Benguela. This happens fairly frequently. The bottom water oxygen concentrations get so low that rock lobster are forced to walk out of the sea. It actually happened earlier this year, and the quantity or the number of organisms leaving the ocean was absolutely astronomical. So this, of course, has socioeconomic implications for South Africa, as well as being detrimental to our ecosystems. And importantly, the oxygen depletion on the southern Benguela shelf is driven by biology. Okay, so nutrients upwell to the surface, they support high levels of primary productivity. That organic matter sinks to the shelf bottom, which is relatively shallow, as I said, and then is broken down by bacteria, decomposed by bacteria, which uses up oxygen. Okay, and that's how the oxygen is removed. And this is one of the major differences between the southern and northern Benguela. In the northern Benguela, at certain times of year, the system is fed by a low oxygen water mass that comes onto the shelf. In the south, that is not the case. The source water to the southern Benguela is subantarctic mode water, which is always well oxygenated. So the oxygen dynamics in the southern Benguela are largely accepted, or they are accepted to be controlled by biology. Okay, but more on that to come. So another thing to know about the southern Benguela, which will be relevant to our findings here, is that I know this figure on the left is a little confusing, but it is characterized by these very powerful equatorward flowing fronts. So if you imagine that you have upwelling coming up the coast with the Ekman layer being moved offshore, at the same time, we have these fronts that move from south to north along the coast. Okay, so these fronts are set up by very strong gradients in sea surface temperature. And they are really strong. They act as barriers to offshore transport. So in other words, where you have a front, the surface layer is actually forced to subduct slightly beneath the front, and you don't get particles or organisms easily being moved offshore along with the upwelling water, right? You have these fronts acting as almost physical barriers to offshore transport. The fronts are surface features. This is important. They don't manifest all the way down to the bottom, all the way down to the shelf, but they nonetheless exist on this coast. And I will talk quite a lot about this most inshore front. It's called the upwelling front, sometimes the Columbine front. And then along the shelf break, so at basically the 300-meter isobath, another front gets set up, which is called the shelf break front. And then finally, at the edge of the subtropical gyre, because of course, offshore of the Benguela upwelling system is the South Atlantic subtropical gyre, we have another front called the oceanic front. For my purposes today, that's less important. But these are set up by changes in sea surface temperature, which you can imagine those gradients are significant, right? Because you upwell water that's maybe 10 to 12 degrees Celsius, but the Benguela is located at 33 degrees south, roughly. So the surface waters can be significantly warmer than that if you don't have upwelling. And this is just to show you this next plot when it appears. Okay, there we go. So what I'm showing here is temperature and salinity, temperature on the Y, salinity on the X, just in summer and winter, to make the point that during summer where you have active upwelling, what you're looking at are data from the different regions of the shelf. So inshore, very much inshore, is are the waters most affected by upwelling. You can see they have the lowest temperatures and the freshest salinities because they're mostly associated with subantarctic mode water. Then you've got midshore waters, which would be between the upwelling and shelf break fronts, and then offshore between the shelf break and oceanic front. And the point I'm trying to make is just that in summer, because we have this active upwelling, there's much more of a distinction between these different zones on the shelf, whereas in winter, they start to merge because the temperature gradients break down, right? You have less upwelling, so the most inshore waters are warmer, but it's winter, so the more offshore waters are cooler. And so what happens in the winter is that the fronts tend to merge and move offshore. So that's really what you need to know, that we have these fronts, that they're very strong, and that in winter, they can merge with each other and be located further offshore. All right, so we regularly sample in the Southern Benguela upwelling system as part of a government program monitoring the lines you see here. These are repeat hydrographic lines. So in total, there's 44 stations. Each one gets sampled from the surface to the bottom 4 times a year. And I'm going to sort of show you data interchangeably from the different lines, but the take-home messages are the same. Okay, so it doesn't really matter which line I show. And I'm just going to show samples collected in summer versus samples collected in winter. I'll try to use summer and winter, but in case I slip up, February for me is summer, and winter, in this case, the sampling was in May. Okay, so just to first sort of acclimate you to the physical or the hydrography on the shelf. So what you're looking at in all of the plots, I have quite a few that look like this, is that you're looking at, on the y-axis is longitude. I mean, sorry, on the x-axis is longitude, but really it's just it's offshore to inshore, and then depth. And you'll see that the depth axis is not linear. Summer at the top, winter at the bottom. Okay, so what you can see is subantarctic mode water, SAMW, upwells inshore. These triangles are all marking the positions of the fronts. So in summer, we have active upwelling of subantarctic mode water inshore, and then this overlying water mass, which is South Atlantic subtropical mode water. The name really isn't that important. It actually derives from subantarctic mode water in any case, also upwells. In winter, subantarctic mode water does not upwell, but you often get the South Atlantic subtropical mode water sort of outcropping at the surface. Okay. And the reason I bring that up at all is because subantarctic mode water is therefore the ultimate source water to the region. Okay, so now I'm showing the nutrient concentrations. This is the only time I'm going to show you all the sampling lines, but I just want to make a point here. So on the top, you're looking at nitrate concentrations, on the bottom, phosphate concentrations. Okay, and the only thing I really want you to note looking at this is that the concentrations of the nutrients on the shelf, I really hope you can see my cursor. I don't know if that's true or not. But the nutrient concentrations on the shelf are higher than the nutrient concentrations in the subantarctic mode water that upwells. Okay, so if the nutrients were all being supplied just by upwelling subantarctic mode water, then the on-shelf concentrations would be the same as in subantarctic mode water, and that is not the case. And we see that across the board for nitrate and for phosphate, right, at all the lines. And that was in summer, and in winter we see the same thing, although arguably in winter, this excess nutrients, which we could call it, extends further offshore. Okay, so we seem to see, for example, in the top left-hand plot, the nitrate extending further offshore towards the more offshore front. So I'll just quickly flip. See here in summer, the bolus, I could call it that, of high nutrients is closer to the coast, and in winter it's further offshore. Okay, so the take-home point, nutrient concentrations on the shelf are higher than in the source subantarctic mode water. And we can actually quantify the extent to which those nutrients are higher. So all I've done here is just to make the point that the nutrients on the shelf are in excess of those in subantarctic mode water. So anything that's not purple, light or dark purple, is in excess of the nutrient source. Okay, nitrate at the top, phosphate at the bottom. Not really giving you any new information than what I said previously. So where are these nutrients coming from? Well, I already told you that the reason that you get low oxygen in the southern Benguela has to do with biology, all right? And that is the reason that these nutrients accumulate on the shelf, is that this image over here is just a very simple cartoon showing that nutrients are supplied to surface waters. Photosynthesis happens in surface waters. It creates organic matter that then sinks to the shelf bottom. The shelf is relatively shallow, so most of the organic matter makes it to the shelf bottom, and that organic matter is broken down by bacteria, which uses up oxygen and produces nutrients. So at this point, I just want to take a moment to say that one of the processes that results in the production of nitrate in particular, okay, as part of the remineralization process, is nitrification. Nitrification is where ammonium itself produced from the decomposition of organic nitrogen to ammonium by bacteria. Ammonium is then oxidized to nitrite and then nitrate. And this process actually uses up CO2, a small amount, but it uses up CO2. Okay, but if the nutrients on the shelf are coming from in situ remineralization, then there should be a relationship between the accumulation of excess nutrients and the biological utilization of oxygen. Okay, and some of you may be familiar with this idea. If I could get sorry, there we go. We can quantify this looking at something called apparent oxygen utilization. Apparent oxygen utilization is just a way to measure the amount of oxygen being used by biology. Okay, so it takes the amount of oxygen you would expect in the water column based purely on its physical characteristics like temperature and salinity and pressure. And it subtracts that from the observations, and any difference must be oxygen that was used by biology. And if we compare, now I'm showing you phosphate again on the shelf for summer on the left and winter on the right, but in the bottom panel, I'm showing you the amount of oxygen utilization.
Just you have 5 more minutes, okay?
All righty, that's fine. I'm showing you oxygen utilization, okay? And what you can see is that they mirror each other really, really well, okay? So the breakdown or the accumulation of nutrients on the shelf is coming from biology, from remineralization of organic matter. So we call this nutrient trapping, where the idea is that subantarctic mode water upwells into surface waters. It supports high levels of productivity. The organic matter formed from this productivity rains down onto the shelf and is decomposed to form regenerated nutrients. And why this matters is because every time you get upwelling again, your subantarctic mode water would then acquire these excess nutrients and bring yet more nutrients to the surface. So one of the questions that has been asked about the southern Benguela is how it can be so productive given the subantarctic mode water source of nutrients. And one of the answers is that, well, you have this regenerated pool of nutrients that can be upwelled to the surface. But there's always been some curiosity as to how this actually works. Why don't you just export the organic matter offshore? And so what we propose is that the fronts are key to this, because if you have these hydrographic fronts that set up a barrier to offshore transport, you increase the amount of time that the surface water spends trapped between, for instance, the coast and the front. And that gives time for the organic matter that's formed in those waters to sink to the shelf bottom. Okay, so we propose that nutrient trapping mechanistically occurs because you've got these equatorward flowing hydrographic fronts. All right, and we can actually calculate that as a result of this, more than a third of the nitrate on the shelf is actually produced in situ in summer, and almost half of it is produced in winter, and that this is a large reason why we get these events of on-shelf hypoxia. So why have I told you all of this? Well, before I get to that, the other surprising thing is, even though I just told you that the nutrients accumulate on the shelf, so we have excess nutrients on the shelf, relative to what we would expect based on stoichiometry, okay, based on the relationship of nitrogen to oxygen to phosphorus, we actually have a nitrogen deficit on the shelf. So the nutrients accumulate, but they accumulate less than you would expect based on how much oxygen has been used up. And this tells you that denitrification is happening. Denitrification is a process by which nitrate is used for organisms to breathe instead of oxygen. And so it only happens under very low oxygen conditions. Okay, so this process of nutrient trapping that I just described has implications for CO2 production. This is a greenhouse gas session. So one of the things that happens when you remineralize nutrients is that you accumulate CO2 on the shelf. And then, of course, and CO2 is produced by both the aerobic remineralization that I described, as well as denitrification. And then every time you upwell, the CO2 is supplied to the surface in excess of the equilibrium concentration, and CO2 will be effluxed to the atmosphere. But the other thing that could happen, and that has become recently a sort of very popular topic, is that these eastern boundary upwelling systems are hotspots for N2O production. So N2O is a greenhouse gas, as we know. It has far more greenhouse potential than CO2 on a per molecule basis, maybe 300 times the greenhouse potential of CO2 on a per molecule basis. And unsurprisingly, because it comes from some anthropogenic sources, the atmospheric N2O concentration is rising. And this pie chart here is just showing you that around 22% globally of the N2O fluxes come from the ocean. This is obviously a natural source. And that about 20% of the ocean's flux is from these eastern boundary upwelling systems. Remember, they're only about 1 to 2% of global ocean surface area. So they're hitting above their weight for N2O production as well. And a recent meta-analysis came out in 2020 that said, that concluded N2O hotspots, N2O production hotspots occur in eastern boundary upwelling systems, but there was actually not a single measurement in that meta-analysis from the southern Benguela, which is an interesting point. Okay, so if I can move this forward. So one last point before I show you our data is that N2O is produced in the ocean by nitrification and denitrification, which is why I introduced these processes. And it happens when nitrifiers experience low oxygen conditions. Okay, they don't like to be in low oxygen conditions. So instead of properly nitrifying, they instead produce N2O. And similarly, when denitrifiers experience low oxygen instead of zero oxygen, it also makes them unhappy, and they reduce nitrate to N2O and not all the way to N2 gas. Okay, so under low oxygen, so hypoxia, it's sort of prime for both nitrification and denitrification to produce N2O. All right, so here again, I'm showing data from the southern Benguela. AOU again, so oxygen utilization in the top panel. Delta N2O, which is just N2O in excess of what you would expect, has been brought by the source waters. So it has to be produced in situ on the bottom. And you can see that N2O production correlates very nicely with where we have a lot of biological oxygen utilization, perhaps unsurprisingly. Okay, but this has never been shown in the southern Benguela before. And we see this in 2 different seasons. And if we calculate the ocean to atmospheric flux, it's not very high. Okay, we get anything from 0 to about 9 micromoles per meter squared per day, which if you compare to the Peruvian upwelling system is absolutely trivial. And to the northern Benguela is, on the low end. But here's what I want to propose, is that based on what we've been finding about nutrient trapping in the southern Benguela, the fact that you accumulate low oxygen, high nutrients on the shelf, and we also know that we have high rates of nitrification happening on the shelf, as well as denitrification happening on the shelf because of the nitrogen deficit that I showed you. You're getting this really high N2O production that's being driven by this process of nutrient trapping. But at the same time, this region is characterized by pulsed upwelling, which means that every time, so we have upwelling, you form organic matter, it sinks to the shelf, it gets remineralized, you use up oxygen, produce nutrients, produce N2O, you upwell again, and you efflux that N2O to the atmosphere, and it happens again. You support productivity, organic matter sinks, you remineralize it and produce more N2O, and you then upwell again and efflux that N2O to the atmosphere. So we are proposing that the simple calculation of a flux based on, a few observations is incorrect, and that because of this process of nutrient trapping coupled with pulsed upwelling, you're actually going to get the amplification of the N2O flux in the Benguela, in the southern Benguela. And this is something that we're starting to go after, and that it could be a much more important source of N2O to the atmosphere than has previously been suggested based purely on models and not on any sort of data. And I will end just by saying that one of the things that we're also interested in understanding is what's primarily responsible for producing the N2O. So I've said denitrification will produce it, so will nitrification. And if we look at these plots, we're seeing that as the oxygen concentration goes down or the amount of biological utilization goes up, so the N2O concentration, so more N2O is produced, or as the N deficit goes up, so more N2O is produced. All of these are suggesting, it's probably some combination of nitrification and denitrification. And why we might care about that is because denitrification produces CO2, whereas nitrification uses up CO2. So if you're really interested in both of those greenhouse gases, we want to know what process it is. And the way that we're starting to get at that is using the site preference isotopes of N2O. I'm cognizant of the fact that I should stop, so this is my last point. So N2O is an asymmetric molecule, okay, which means that it's an N, and an O, as opposed to NON. And whether or not the N15 enrichment or the isotopic enrichment that can happen is on the outside or the inside N atom can be determined by the process producing the N2O. And so we can use this idea of site preference to try to get a handle on which process is primarily responsible for N2O production. And we're still sort of very newly investigating this, but based on what we found so far, it seems that in the summertime, the dominant process is denitrification. And in the wintertime, there is more of a contribution from nitrification. How that will stand up at this point, I'm not sure yet, but I just wanted to give you a sense that we can start to get at which process is most important. All right, so to conclude, I know I gave you quite a lot of information, but so what we've found so far is that the hydrographic fronts that occur, so the physics of the Benguela, of the southern Benguela, mechanistically allow for nutrient trapping, and this nutrient trapping actually results in there being higher productivity in the southern Benguela than you might otherwise expect, because every time subantarctic mode water upwells, it entrains these excess nutrients back to the surface, and that there are going to be very strong implications of this for hypoxia, because the more productivity you have, the more nutrients you regenerate on the shelf, the more oxygen you use up. And I've shown you that this results in the production of CO2 and N2O, and that we propose that the pulsed upwelling, the pulsed nature of upwelling in the southern Benguela likely amplifies the N2O flux to the atmosphere, although we need to do quite a lot more work to actually show that. At some point, the oxygen concentrations on the shelf could get so low that you'll start to consume N2O. So the only biological sink for N2O is denitrification. Once you get to anoxia, denitrification will consume N2O. But at the moment in the southern Benguela, we don't have that. We only have hypoxia, which turns out is like the sweet spot for denitrification and nitrification producing N2O. And then, of course, the challenge is what happens in future. If upwelling intensifies, as it is predicted to do, what happens? I mean, do you support more productivity, so more sinking organic matter, more oxygen depletion, more CO2, more N2O? Or do you have, more intense upwelling means less time for waters to be at the surface before they're advected offshore? And again, as coastal waters experience deoxygenation, yet more deoxygenation, what happens then? And so I'll leave you with those thoughts. I'm happy to talk about them at any point in the question and answer session. And again, thank you for inviting me.
Thank you very much. It was very interesting, very fascinating work. We're a bit behind schedule, but this means that we will have bit less time for the questions and answers. But I'm very happy to introduce our coming lecturer, Fei Chai, from the Second Institute of Oceanography, who will talk about ocean-based carbon dioxide removal. Thank you, Chai. Fei. And
thank you very much,
thank you,
and good. All right. Good evening. Good morning. Good afternoon. And so I'm going to talk about a ocean-based carbon dioxide removal. So we have heard about a greenhouse gases and then accumulation of a carbon dioxide in the atmosphere. How can we remove and then store more carbon in the ocean? So I'm going to talk about three things. It's really why we are doing this. And so it's a sense of urgency, and we have to do something to avoid a disaster. The second is really the ocean-based CDR, the carbon dioxide removal. What are the methods? What are the latest thinking on various techniques? And then I'm going to use ocean iron fertilization as an example, because we have done so much research on this subject for the last 30 years. And then from the laboratory, this theoretical work and the hypotheses, to the open ocean iron fertilization, to the engineering implementation of this. And then the conclusion, I think, is very simple, is we need to do more research on any of this ocean-based CDR, including the iron fertilization. And then so, I can control. So the news media goes the cycle so fast. This is last November. And then there's a COP26, the Glasgow, the climate pact. Finally, they reached this agreement, and then the reason is this: each country that commit the greenhouse reduction, and by the screen is not working, by this. Sorry. So it's really, we need to reduce more by 2030, and then we need to reduce 45% of the greenhouses, the levels compared to 2010. So each country's commitment is really not there yet. So we are way far. So in order to get to this part. So this is really created a series of the prompt. I'm sorry, I have a trouble to control my cursor here. All right, so this is April, the IPCC, the AR6 report. And then, so this is the newspaper coverage is really, we will have to do something, act now, otherwise it will be too late. I think this is really the part we have to do something. On the other hand, the world is getting warmer, and Sarah is already talking about. This is the temperature record for the last 40 years, and then you can see the keep going up the temperature, and then also, and then from the records for the warmest the 10 years, 9 out of 10 years occurred during this the last decade. So this is really the part that is the world is now waiting for us, right? So this is the latest. This is the Northern Hemisphere, the average of the temperature, and then for the 2021, you can see it's already increased up to 1.6 degrees centigrade. So this is the IPCC report. By the end of this century, the world as a whole, we want to control at a 1.5. The last summer, we already reached that part. But temperature is only one factor. It's really the hydrological cycles, the floods, because the warming, and then they are occurring more severe and more often. This is the report. This really this climate disasters compared to the last 40 years, and this 1980 to 1991, and 2000 to 2019. So you can see this is really the part, the floods increased by about a factor of 3. The warming also increased by a factor of 3. So the storm increased by about 50%. So this is regardless where you are, whether it's developed countries or developing countries, you cannot avoid this part. So this is about 20 years ago, and during this AR4, they already start thinking about this geoengineering, because the trajectory clearly indicated that we cannot rely on the countries cutting down the emissions. We have been talking about this for the last 20 years. We're still not there yet. So this is 20 years ago, we start already thinking about this geoengineering, back then they called it. It's really the 2 parts of it. One is a solar radiation management. So this is really the part that physically can we reflect more solar radiation back to space, that including in the stratosphere releasing the sulfate particles, or putting the space mirrors, or paint all your houses white, etc. The other is the carbon dioxide removal, both based on land and also in the ocean. So this is really the part. Since then, there's been a series of reports for the last 15 years, and then issued this, we need to do more research and looking into various techniques on this subject. And then, so this is really the part. Since then, the ocean community and then have been acted together. Well, we want to focus on the ocean because the ocean has a tremendous potential to take up more anthropogenic CO2 from the atmosphere. We take on annual basis about 25%. Now we accumulated and over about 40% of anthropogenic CO2 because the reservoir is so large compared to land and the atmosphere. And so that's why the ocean has a huge potential to store carbon dioxide. Not only that, but it is also, once this atmospheric carbon dioxide entered into the ocean, if they can somehow export across say 100 meters depth, so they will stay there for more than 10 years. If they cross say 300 meters, the depth, they can stay there for up to 100 years. So this is really the potential. Think about the land. You plant the grass and the trees, and then what's the lifespan of the terrestrial vegetation? So on average, maybe 30 years or so, right? So the ocean has a huge potential that to take up atmospheric carbon dioxide, transport it into the depths and stay there for a longer period of time. So this is why the ocean has a huge potential to do this part. So the ocean-based CDR is really, this is a report issued a couple years ago. There's several methodologies, and then including the blue carbon near the shore, you plant more mangroves, and or you plant macroalgae, and or you do the iron fertilization and or alkalinity enhancement, and then or you do the artificial upwelling. You bring the nutrients to the surface to stimulate a phytoplankton production, and then export as a particulate organic carbon. So this is a pretty solid nature-based phenomena and then the ideas and theories. So it has been in the nature how it works for a very, very long time. So therefore, this is the really the part. Okay, so this is the last year, the National Academy of Science in US released another report, examined all those methods. And so you can download, I can share those reports. And then, but the media is really not ready for this human intervention, say you planting, say do the iron fertilization, or you putting hundreds of the upwelling pipes that bring 300 meters nutrients to the surface. So the public is really not ready to accept this. This is more like you know, science fiction movies and etc. So there's a lot of public outreach to do on this subject. So I have been involved for about 3 or 4 years for this, they call the GAZAMP group. This is really all the United Nations organization, and they select a group of experts on those subjects. And then we worked on this for 3 years. It's really the high-level review of wide range of a marine-based CDR. And so we spend about 2 weeks each time, and then to discuss this. And then, so this is really the part we talk about this, and then we come up this reports, and then this is published a couple years ago. This is the methods on the left, and then so this is the really the examples where they come from, the source of the evidence-based knowledge, whether it's a nature-based phenomena, and then how have you done the field test, and then what are the needs, the regulation. If you dump hundreds of thousands of tons of iron into the ocean, who's responsible? Who is doing this monitoring? And then, so those are all the issues we discussed. So any marine-based CDR, it goes through the 7 stages in order to implement, to be effective. So first is the concept, where they come from, right? So whether it is you based on the past evidence, the paleo records, or some phenomena, how have you done the test? So you do this laboratory study, for example, the iron. You have 2 control experiments. One bottle you add iron, the other you don't, and you compare the study. And then can you model this, quantify it, right? So this is very important, because any mature science, you have to quantify it, right? So develop into the set of models. Have you done the field studies? Can you examine a side effect, whether you stimulate more phytoplankton growth when they sink, they consume the oxygen. And so if this massive phytoplankton bloom due to the iron consume the more oxygen, so they make this a deoxygenation much worse. And then can you do the modeling and the scaling up? You do this 10 kilometer by 10 kilometer site. Can you model this up to 100 kilometer by 100 kilometer? And so this is etc. And then by the end, can you implement at a large scale and to be a meaningful and effective to take more carbon dioxide from the atmosphere? So those are the issues we discussed, and also the code of conduct. Any manipulation of the natural system, we have to have a good intention, and then we have to have the governing structures in place to avoid this a negative impact. Although we have performed the largest engineering for the last 200 years because we mined our coal from the mountains, we drilled from the deep sea. Those that really we called human engineering, alter the nature, right? So, but this is the, and then consequences is the greenhouse gases. So those are the issues we have to look into it. So in the ocean, 30% of the areas are those so-called high nutrients and low chlorophyll, HNLC regions, because they're far from the land. And then the amount of iron supply to the ocean is from the land, and the dust and etc., the sediment, etc. So in the middle of the subtropical gyres, there are low nutrients and low chlorophyll, right? And then combine those two areas, they are about more than of this part. I'm not quite sure. I mean, your count is correct, but okay. All right, so this is the iron. And then, so this is the John Martin's hypothesis. And then this is really from the Paley record, from the glacier and the interglacier. This is the famous Martin iron hypothesis. It says, it gave me half tank of iron, I give you ice age. This is this is about almost 30 years ago, we started to discuss this. And then where the iron come from to the ocean? The number one from the sediment, because this is recycled and near shore. That's why the coastal regions has a lot of productivity, the iron. But the dust is also important, both the natural dust and the human activities. I give you one example. This is the dust from China. And then you can see this dust, and it goes through Pacific and go around the world in 2 weeks. And then there's a lot of the iron behind this dust storm. And then they deployed the floats. The floats can measure the chlorophyll, can measure the POC, and then sometimes you have to be lucky. And then they, right after the dust, and they caught this increase of the POC, and then due to the deposition of the iron, then it lasts for 2 weeks. And then, so this is the one examples. The other is the volcano. The volcano eruption, and then this is also in the North Pacific, Aleutian Islands. This volcano eruption is 2008, and then the Gulf of Alaska, lack of iron. So you can see, and during the month of August, the chlorophyll increased by about a factor of 3. The PCO2 dropped by about 30-40 ppm. And then this is really the one of the examples, and then to show this volcano and the dust. The last one example is a fire, the forest fire. This is the Australia forest fire, and all this ash, they burned and they transported into the Southern Ocean, which is really the part of the Iron Limited. We follow this track of the ash, the forest fire. You can see in this region, the chlorophyll increased by also about a factor of 3, and compared to the normal conditions. And we look at the aerosols, and we look at the daily chlorophyll, you can see this is a significant increase. And then you can calculate of how much the carbon emit from the forest fire is 320 teragrams carbon. And due to the phytoplankton increase, and then they absorb roughly half of it, 50% of this part. This is the one in the middle. And then, so this is another part is really the human activities, the artificial upwelling. So we conduct 14 such events. And then the latest is the 2012. And then for the Gulf of Alaska, and they dump 100 tons of iron. And then, that we look at this, and then from remote sensing, and then we can see in the middle of the eddy, they dumped 100 tons of iron. We saw a increase the chlorophyll by a factor of 10, from 0.5 milligram to 5 milligram. So this is really the part we compared a volcano eruption. This is really the part, a factor of 3 increase. And then this is the effect of 10. This is the artificial upwelling, artificial fertilization. And then you can see the scales are different. And then, but anyway, this is really the example. You can compare the natural versus the part. And the New York Times talk about this. So to summarize it, and then we have done 14 of such events. And then we all saw the chlorophyll increase. We all saw PCO2 decrease, take up more carbon dioxide. We need to do more research on this, especially the large scale. And so the latest, I think, I'm not quite sure the timing here is correct, but I'm finishing up. And then because according to my time, as 20 minutes, but I'm finishing up. This is the latest. And then we form a consortium, and we meet on the monthly basis. We talk about how to design the next iron fertilization experiment. And then based on the past experiment, we then choose the Equatorial Pacific. And we have the latest models, including the iron, and we artificially put an iron into the model, and then to see how the currents take the iron downstream to stimulate the phytoplankton, especially the diatom growth. The lower part is the diatom growth. And then we calculated how much iron we can release, and then how much the PCO2 they can export. And so this is we have done quite a bit. The bottom line there is 1 ton of iron can stimulate 5,000 tons PCO2 export, 1 to 5,000. So that's why we talk about this. Anyway, this is the latest. We need to deploy all the latest of the observational capabilities, the modeling, and then this is my summary slides. Okay, all right, I stop here.
Hi, okay, thank you very much. Very interesting summary of the topic. So we had I think we have a nice overview on what was done, where we stand, and possible activities. And now we have some time for questions and answers. So I don't know, whoever wants, I think we can. So first, I suggest if it's not complicated for you, I mean, open the cameras. It would be much nicer to see each other, at least the videos. And so yeah, so whoever has a question, I think can try, and let's see how it goes. If not, we can, I think there were questions in the chat, right? I didn't pay attention yet. Okay, so I don't see almost anyone here. So does anyone wants to start?
Hello, everyone. Can you hear me well?
Yes.
So, my name is Mariana. I have a question for Sarah. How could you say if we have a strong atmospheric phenomenon, it would interfere in the NO2 release to atmosphere? No, I don't know.
Yes, so I mean, you mean if you had sort of a storm, a very powerful storm event or tropical cyclone or something like that. Yes, absolutely. I mean, any enhancement of the physical processes that ordinarily characterize the upwelling would presume, if they bring these waters to the surface, would presumably enhance the release of N2O, but you can only release as much N2O as you have in disequilibrium, right, between the surface waters and the atmosphere. So those would be sort of stochastic events where you might see a pulse of N2O being released, but I don't think they're going to dramatically enhance the N2O flux unless they're somehow accessing N2O in excess of the surface equilibrium concentration and bringing it to the surface. So if they're ventilating, N2O that would otherwise not be ventilated, absolutely. So yeah, I mean, it's always hard to try and quantify the impact of these while large, more stochastic or less frequent events. And I will say that, I mean, that in itself is a motivator for having a better handle on the background state in some way, like the Southern Benguela, where we have very little information at all about N2O production. So we don't even have the baseline, right? And we don't even have a great model for inferring it, right? Most of the models of the Southern Benguela that try to couple physics and biogeochemistry, they don't have the sediments in them, for example, which turns out pretty important for the biogeochemistry. So it's a great question. I gave you kind of a hand wavy answer, but I think that's kind of the state of things right now.
Am I missing someone? I have a question for you, Faye. So where do you think we stand in terms of actually implementing these solutions on an operational level?
Yeah, it really depends. Different groups and the scientists that have a different favorite places.
Sure.
And okay, so but I think operationally you want to be closer to islands or lands. You can transport your iron. Number one. Number two, I think you want to take advantage of a growing season of the ocean. Southern Ocean is vast. It's a great, but half of the year there's no light. The light is really extremely limiting. It's hard to operate. But having said that, I think the Southern Ocean, if you can manage 4 months out of year, and the light part and also the temperature part. The North Pacific, the storms, one after another. And so that's another part. If you ask me, my favorite place is the Equatorial Pacific. That's where we have done 2 experiments already. And then that's where we have the monitoring moorings, BGC Argos, and then so far from the land, the currents get away from the islands, so you don't have much of impact on the islands. So I give you 3 different answers.
Yeah, no, it's good. And can you estimate or guess how is the likelihood of actually implementing these solutions? I mean,
Yes,
where do we stand in terms of
yeah, okay,
implementing science
sure,
and
sure.
policy?
Yes, okay. Yeah, actually, I've been working on this. There's so many graduate students. When I was a graduate student 30 years ago, and I worked on this, and then I'm still working on this. And then so I think that this topic is never getting old because there's so much we can learn, especially the fascinating to remove carbon dioxide from the atmosphere. So the latest thinking for the last year or so, there's a series of resources going to the marine-based CDR, and not only from the government, but also from the private, the foundations, and etc. They realize we have to do something, and you cannot just solely depend on the cutting down the emissions. We have to remove the carbon dioxide from the atmosphere. You can grow so many trees, but eventually you run out of space on land. So there's a pretty series of resources and thinking going into this area now.
Okay, interesting. Anyone else?
There are 2 raised hands. Just want to point it out.
So yeah, so please do. I don't see them actually.
So if you open up the chat, I mean the participant list, you will see. But I see Anna and Raisa. If I say your name right? I hope I say your name.
So let's do by this order.
Okay, so that was me first then. Thank you for all the presentations. It was really interesting. I was a bit curious about the iron fertilization. Like, how will that work in practice? Would this be transported by ship then, or? And also, as a follow-up, have you identified any specific risks associated to this, or? Thank you.
Yeah. Yes. Actually, there's 3 modes of delivering iron. One is a traditional one. You send the ships, and then you spread them around, and the second one we call the barges, the large, those platform, the barges. You stay in one place, and they let the currents and the carry. It's more mimic as an island, as an island effect. The last one is use this giant airplanes. And then, so the airplanes and load the iron, spread them and the low altitude, and we compare the cost. And actually the airplane is most effective in terms of the cost of delivering compared to the ships. The barges is in the middle. And so to answer your question, and to address the associated risk, we have to do the monitoring, the environmental monitoring, not only the patch area, but it's also the downstream. So you have to do the monitoring in place before you can calculate and count the carbon. So we have to do that. Otherwise, you cannot get approval to spread the iron into the ocean. So you have to have the plan to monitoring to do the risk assessment.
So who's next?
Hi everyone. My question is to Professor Chai as well. I was interested about the alkalinity enhancement technique. I've heard about the iron fertilization, but how would it be possible to increase the alkalinity in the ocean? And do you think that would be more effective than the iron fertilization or not?
The good question. They also mimic the natural phenomena, and it's really the carbonated system, and you add more calcium, and then you change the pH, and then you change the PCO2, and etc. And so they talk about the olivins, the grind them up and spread them, and then to really change the pH and then change the PCO2. but it's a really the mass one-to-one calculation. So 1 times you change the alkalinity and you change a 1 part of the PCO2. So it's the mass you have to. So in order to take 1 ton of the CO2, you have to do roughly about 1 ton of the alkalinity, the material delivered. So the cost of doing it is much, much higher than the iron. The iron 1 ton, based on our current model, can up to 5,000 or even 10,000, depends on the location. So that is really the economic calculation of this part.
Okay, I don't see any hands. Krista, am I missing someone? Okay, so last chance. So I think we can thank our lecturers and go on a break. We have 20 minutes.
There's a hand.
Oh,
there's a hand. Lisa.
Ah,
Lisa. Lisa.
Lisa. Yeah.
Lisa.
So sorry, there we go. Am I on?
Yes.
Yes.
Yeah. So, sorry, Faye. I just thought I'd jump in since there weren't any other questions. I'm wondering. It's been a while since I was looking closely at the iron fertilization stuff, but something I remember about it was I thought that if it were actually successful, if the particulate carbon actually enough particulate carbon to make a difference to the atmosphere were to sink out, and then but then it could actually contribute significantly to the deoxygenation problem. And so going back to what I think it was Anna was asking about, or the risks. I mean, so what's the balance on that looking like these days?
So we have been studying this very carefully. It really depends what kind of phytoplankton groups you're stimulating. If you're stimulating enough diatoms, and then the aggregates, they sink as a rock much, much faster before they can get this a large portion being remineralized. Okay, so I think this is really the key. In the past, we never saw or studied this very carefully, right? Except the Japanese, the experiment, SEEDS-1, the chlorophyll increase up to 20 milligram per cubic meter, and that was a diatoms. When the diatom blooms, they sink very fast. They escape all these twilight zones, basically, right? So between 100 to 1,000, especially when they aggregate. So this is really the part, this latest thinking. Can we stimulate a large diatom blooms and let them to escape of this twilight zone much faster? And so this is one part of it. The other part of it is really this current, the role of the currents. You have the particle sink, but if you have a strong enough of the currents, and then they get spread, and instead of localized deoxygenation, so they spread by the physics.
Okay, thanks.
Okay. So, am I missing another one? I don't think so, right? Okay, so we have now a 15 minutes break, and we will meet again at 12 o'clock for the practicals. Okay? See you soon. Ooh. Okay, so I think we can continue. I hope everyone is here. So now we will go to our second part of the day, and we will have an opportunity to. So this would be the case for all of the days. The second part would be we'll have some practicals, and today we'll have following the lectures in the morning session. We'll have an opportunity to explore, to practice the exploration of marine carbon cycle and data analysis of PCO2 and carbon fluxes. We will start with with a short presentation and some small group discussions. And this would be led by Marcel de Plessis from the University of Gothenburg, Ute Schuster from the University of Exeter, and Toby Steinhoff from Geomar. So I let you pick up from here.
Thank you.
Okay, good.
And welcome everybody. We have 55 participants. Are we waiting a bit longer or should we start?
Maybe we can wait 1 or 2 minutes. So just let me just say that after this this session, this practical session, we will have a short break, another short break, and we will meet again for the poster session at 5 past 2 o'clock. Okay, so 2 p.m. Just in case people, just for you to know. Okay, so after the practical, our next session, the poster session, will be at 5 past 2. And I think you can start.
Okay. Now I'm getting a message that the host disabled participant screen sharing. Paul, I had put the presentation in the shared Google Drive.
I dare to say that we've changed things now, so you should be able to share your own screen and drive the practical yourself.
Okay. Here's our title screen. Is that visible to everybody?
Yes.
Okay. Right. We had already a introduction to this, so I will move on. And actually, the first thing, we had prepared some polls, which are on the Rover website, and we had already some replies. So the first, what discipline have you studied? Already very interesting, quite a variety of backgrounds. So that's great. Then have you already worked with observational ocean PCO2 data? Predominantly no. No problem. We will do that later on in a practical session. Then what you think the approximate contemporary atmospheric concentration is of CO2. This is excellent. Some know. Hopefully others will know the answer too through after our presentation and practical. And then how much do you know about the marine carbon cycle? A little, some, quite a lot. Okay, also a mixture. Thank you, Paul. Then I go back to the presentation, and we have seen these now. So we are going through a little background of the marine carbon cycle. First of all, a reminder to some new information for others. And ending with a practical coming after the presentation where you get some data and you can actually do some data investigation and calculation of air sea flux. So some basics at the beginning. Why do we actually care about carbon? This is global and not only for the oceans, but on our planet, the biologically active planetary surface includes the atmosphere, vegetation and soil, as well as surface ocean and deep ocean. Additionally, we have buried carbon, which is deep within the Earth's crust in the mantle, and this includes the fossil fuel carbon. This buried carbon was predominantly not within the biologically active planetary surface until humans started to dig it up and burn it for energy. This has since then added excess carbon to the biologically active planetary surface, which is called anthropogenic carbon. And this causes the multifaceted environmental change, including in climate. So what's happening with carbon? Again, global, not only the ocean. This is a graphic from the Global Carbon Project. For those of you interested, it's a fantastic source of information, specifically about global carbon. So this graphic includes land, atmosphere, as well as the ocean. The arrows are the fluxes between these domains, and the smaller, narrower arrows are the natural cycles going up and down between atmosphere as well as surface and circling around in particular domains. The thick arrows at the top are the anthropogenic impacts. The numbers are actually the amount of fluxes, or the amount, no, here it's only the fluxes. I'm going to come back to this graphic, or part of this graphic, later on. We here in this practical session concentrate on atmospheric and ocean fluxes. The arrow of the ocean is downwards as a net carbon. Again, I come back to that in a moment. And the gray upward ones as the impact of the anthropogenic carbon. The same information, yet shown in a different way, is this graphic, again from the Global Carbon Project, but it's linked to the IPCC reports. On the left are the sources of carbon, which are the anthropogenic carbon to the atmosphere, and on the right are the sinks of this atmospheric carbon. The atmosphere itself is considered a sink for anthropogenic CO2, as well as the land and the ocean. And you see that the sources are not only fossil fuel burning, the top right image, but it's also land use change, which humans have done ever since agriculture has been done in history. And we specifically here then will concentrate on the ocean sink. You see on the right that 29% for terrestrial sink and 26% of ocean sink is about split half and half between the land and the ocean on this planet, and the other half stays in the atmosphere. One important thing to consider, and when you read up about this, you see that a lot of these calculations actually have an imbalance between the sources and sinks, and it's currently about 3%. In order to predict climate change, this imbalance has to come down, and this is why intensive research is being done in this area. So, as mentioned, 3 domains are included in the cycling of carbon throughout the world: atmosphere, ocean, and land. It's a complex cycle, and the whole cycle also includes the so-called land-ocean continuum. and that is the transport of carbon from the land to the ocean via rivers and estuaries. And the atmosphere, of course, is another link between domains, i.e. the land and the ocean. The ocean role in mitigating climate change. This on the left is part of the image I showed earlier. And the ocean is a net sink of CO2, anthropogenic CO2, which is the green thick arrow going downwards. So currently in the contemporary CO2 cycle or carbon cycle, the oceans are taking up more CO2 than they release to the atmosphere. The natural exchange, of course, happens as well, which are the narrow arrows along the thick ocean arrows. That is going on top of it, and the anthropogenic excess addition of CO2 to the atmosphere is the thick gray arrow. Without this role the ocean has on this planet, climate change would have been and would be significantly stronger than it is now. And the top right is an image, classical so-called Keeling curve, measurements of atmospheric CO2 from the Mauna Loa Observatory in Hawaii, the increase of CO2 in the atmosphere, and this increase would have been substantially higher without the ocean uptake of CO2. So it's a crucial role the oceans play within the global carbon cycle, as well as in mitigation climate change. Now, a bit of marine chemistry. You don't need to be a specialist in chemistry. The ocean net sink is due to several things, and that includes the chemistry. The image here is a summary of the carbon chemistry in the ocean, combined with biological activity and physical water movement. So it includes impacts and influences from many, many different disciplines, and everyone who researches the ocean carbon cycle has to at least know something about this. One effect you might have heard about is the formation of hydrogen ions in orange, yellowish highlighted in the graphic, which leads to a change in the seawater pH, and that is called ocean acidification. And the importance of that is that it affects, the ocean acidification impacts ecosystems. So this is an impact on the biology in the oceans, which is in the media quite a lot and intensively researched. The other thing, important thing, is that the ocean capacity to take up CO2 is not unlimited. This has to do with the ocean chemistry of carbon, where actually at some point the oceans can be saturated, and that will mean that the oceans won't be able to take up any more CO2. So we as humans cannot rely on this forever. It is not guaranteed to continue forever. Okay, these graphics are published results simply illustrating whilst the ocean carbon content increases, these are the graphics on the left, the seawater pH is decreasing, which is the graphics on the right. And this is measurable in the global oceans. Each graphic is from a different location in the world. So this is not theory, this is actually practice, and it's actually happening and can be measured. During the practical, we have some data for you where you can calculate the CO2 exchange between atmosphere and ocean. So a bit of principle about this before. The so-called sea air CO2 flux, which in mathematics we abbreviate as F, occurs at the sea surface. And an example image of that is here on the slide. And it includes the CO2 in the air, in this, for the SE flux, in the lower atmosphere adjacent to the sea surface. Then there is a very, very thin ocean layer, which is micrometers thick at the top of the ocean. And then it involves also the so-called mixed layer below this skin or very thin layer at the surface. Having information about these things, we can calculate the flux. And we calculate the flux F by this equation 1, which is stated here. Several things is then needed and also calculated in this process. One is the delta PCO2, which is the PCO2 in the ocean surface minus the PCO2 in the atmosphere. K0 is the solubility in CO2. And K is the gas transfer coefficient, which is predominantly estimated by wind speed. You will have a handout for the practical in a short while, and the equations for these steps, for each individual steps, is in the handout. So you will have details about this for the practical. What will also be available to you are the input parameters to calculate the flux. So we provide some data, and these include the atmospheric PCO2, i.e. PCO2 atmosphere, the ocean surface PCO2, i.e. PCO2 ocean, the sea surface temperature, abbreviated as SST, sea surface salinity, abbreviated as SSS, and the wind speed, abbreviated as WSPD. So these will all be available to you in a moment for your calculations. One particular thing to look for in your practical work is the ocean variability. Now, ocean surface carbon, which we concentrate on here now, is not constant in space or time. The images on the right, I'll come back to them, but if you briefly look at them, they just show you that there is variability in space as well as variability in time, which is the top image versus the bottom image. And the reasons for these variabilities, i.e. the drivers of variability, include both spatial and temporal differences. And that is in several other parameters as well as processes. One is ocean temperature, ocean salinity as well. Then, of course, atmospheric CO2, the wind speed, biological activity, for which we have, for example, dissolved oxygen as a proxy, and ocean water circulation, which you've already heard about in the presentations earlier today. So during the practical, you have the opportunity to look for these variabilities because ocean carbon and the air sea flux is not constant. So diving into a bit more into the spatial variability, this image is a global annual mean of ocean surface CO2 flux. And this, I'm using this simply to visualize the spatial variability. So you see that generally speaking, in the tropics near the equator, the oceans are a source of CO2 to the atmosphere. So they are higher in the oceans than in the atmosphere. And at higher latitude, both going north as well as south towards the poles, the oceans are a sink for CO2. So this is generally speaking. You also see regional differences, and earlier in the presentations we already heard about differences specifically about the Benguela upwelling regions. So they are also very smaller space, lower resolution variability in the ocean. The other thing is the temporal variability, and here's a copy of the image from earlier. These are two global monthly mean ocean surface CO2 fluxes, and that additionally visualizes the temporal variability, in this example between February at the top and August in the bottom. Now these are monthly variabilities in these examples, but there are other temporal scales of variability in the ocean, and they include even diurnal variabilities, i.e. daily changes. Then of course seasonal, for which these are the images are two examples, as well as interannual variability, meaning of a much longer time scales over many years, that not each year is the same. You might have heard about influences from El Nino or La Niñas, which have an impact going around the world. These are interannual variabilities. And then of course long-term trends. If you remember the Mauna Loa Keeling curve, this is a long-term trend of an increase in CO2, and we have similar effects in the oceans as well. On to the data sets that we have selected. The first one is from a campaign on board the research vessel Polarstern, and it went from Punta Arenas in Chile to Bremerhaven in Germany. The data sets included in this example are temperature, salinity, atmospheric pressure, sea surface PCO2, atmospheric PCO2 of course. We have dissolved oxygen in this data set as well. Oxygen saturation is related to that, and then the wind speed. And the other data set we have for the temporal variability is from a mooring near Bermuda in the western Atlantic, and this data set includes temperature, salinity, atmospheric pressure, sea surface PCO2, atmospheric PCO2, and wind speed. So to move on to the practical, in this you will be allocated breakout groups to work as teams within with some data, and as a group you will either concentrate on spatial variability or temporal variability. These data are available to all of you, but in the time you've got available for the practical, you should concentrate on one of them. And you have time, and that is until 10 minutes prior to the end of the practical, when we'll come back into plenary and have an opportunity to discuss your findings when you're working with the data, as well as further and question and answers about any of the marine carbon cycle in the AC flux of CO2. And Tobias, Marcel, and by myself will join you in the breakout groups to see how you are doing. Paul will allocate breakout groups, so you'll be joining in a moment. Just before we are doing that, there is another poll we have created. All these polls are staying open, so you have time later on to add your thoughts and comments, but this poll particular, select any that are relevant as potential drivers for the variability in the CF CO2 flux, and this is also on the WOVA website. So with that, on to Paul, and who will allocate breakout groups. And the three of us, Tobias, Marcel, and myself, we will see all of you in your breakout groups throughout the next, what do we have, 70 minutes or so? Yeah, okay. So, Paul, will you do that?
Hi there. Yes, I have now done that. So everyone is on their way out into the groups except for this smaller organizers group here. So everyone else has disappeared off. All the students are in their groups. And I can see that they are mostly there now. I've moved us into 6 rooms. So you guys, the 3 of you should be able to drop in and out. I just want to chat to you first, make sure you are happy with that. So at the bottom of your screen, there's a breakouts button. If you click that, are you able to see?
I don't, oh, just come up. I see it now.
You see it?
Yeah.
So it should be at the bottom, and from there you can see all 6 rooms, and there will be a little join button next to each room. You can go in there, see how the students are doing, and then use that breakouts button again to leave the room and come back to this main session.
Okay, sorry, I missed the last one. Are you calling, Paul? Are you calling everybody back?
We will call everyone back with 10 minutes to go. Is that how much time you'd like?
Yes.
Right. So
if people come back earlier, yes, yes, of course.
okay. So with a
longer break, yeah?
I forgot the break. Yes.
It's okay. Okay, we spoke about them taking a break at a natural point within their groups. So when you do your first round through those rooms, if you could just mention to every room, by the way, make sure you take a break during this section. And that'll be fine. I'm sure they will. They'll be happy with that. Okay,
we have 9 breakout groups. Is that right?
Should be 6. Okay. 6 breakout rooms. So sort of 2 each. If that's how you'd like to split them up, obviously that's down to you. And we will call everyone back with 10 minutes to go, and I'll give you warning of when that's going to happen.
Okay.
Fantastic.
So the 3 of us, I guess we are going to 1, 2, 3.
I just wrote to just for the start, Ute, you quickly have a look at 1 and 2, Marcel at 3 and 4, and I go to 5 and 6 just very quickly to check that they know what they're doing.
Yeah.
And they can pick what they want to do, if they want to do spatial or temporal, or should we force them?
I would say they can choose.
Yeah, just wanted to.
Okay.
Yeah. See you
cool.
later.
See you
okay. See you shortly.
Brilliant. Thanks all.
Okay. I'm guessing everyone is here. So we can start. I think we can just start. So I will not introduce each one of you because because it would take too much time. So each one, you have 1 minute for presenting your poster, and you have the order. So I think I suggest you start. Okay, does it work? Very good. We can't hear you. Right? Is it only me that can't hear?
Yes. I also can't hear.
Hello. Am I audible?
Yes, now we can hear you. I just want to mention I will stop each one after 1 minute. Okay?
Okay. Okay.
It will be tough because otherwise it can take a lot of time. So good luck. Let's start.
Yes.
And present yourself, please.
Yes. Hello, everyone. My name is Nazir Ahmed. I am working in the Geosciences Division, Physical Research Laboratory, India. Today I'll speak about the carbon and nitrogen fixation by isolated oceanic cyanobacteria. As we all know, phytoplankton is the major primary producer in the ocean, and it takes parts to fix the carbon dioxide from the air around 50%. And the among phytoplankton, picophytoplankton group is the organisms which is abundant, highly abundant in the global ocean. And these organisms also require the nitrogen for the growth of the organism. So here carbon fixation and nitrogen fixation is important. So with this objective, I study to measure the abundance of picocyanobacteria, and I will isolate the and characterize the cyanobacteria, particularly picophytoplankton, and how this organism behave to fixes carbon and nitrogen by bulk in the whole seawater and the specific group. So with this methodology, I collect these samples and the filter for the natural carbon and nitrogen isotopic abundance in the specific group, as well as the total phytoplankton, particular POC and PON. With this, I first check the abundance of the picocyanobacteria in the flow cytometer, and after sorting, I collect the sorted samples and culture it, and also perform the manipulative experiments based on the different climatic conditions, such as different temperature, salinity, and the multiple elements such as stress elements as well. And natural carbon abundance and nitrogen abundance in the taxon specific will the poster is gone.
Okay. Okay.
Hello everyone. Namaste and good evening to all. I'm Mahendra Rajwar from Aries, India, and today I am here to present the overview of my research title, that is a study of the non-methane hydrocarbon NFCs in ambient atmosphere or ambient air over the central Himalayan and associated region. Basically, non-methane hydrocarbon are the important play an important role in the tropospheric atmospheric chemistry to the formation of ozone SOA formation, secondary organic aerosol formation. If we compare their ozone formation rate with the other precursor, it is much higher than the other precursor. And because their lifetime is vary from the minutes to the month, so we can use these species as also as the what we get that tracer for the atmospheric lifetime. For this purpose, we have selected the two different sites. First one is over the central Himalayan region at Aries Nainital, and second one is from the IGP region, the Indian Gangetic Plain side, that is Haldwani. And what we compare the inflow from that IGP regions to our side, that is so from the at central Himalayan region, for which we collected the sample from two sites simultaneously, from two different sites, Haldwani and Aries Nainital. For using the gas chromatograph technique, we have observed or separated 14 different kind of non-methane hydrocarbons. For 8 light non-methane hydrocarbons from ethane to isopentane, and whereas BTX from benzene to O-xylene, which contains 3 isomers of the xylene also. And for the gas chromatography techniques, we use that gas chromatography technique to detect these 14 non-methane hydrocarbons. We use FID detector, flame ionization detector, and also we use these observations into our models, the box model, to see what kind of the behavior of these non-methane hydrocarbons in the ozone formation process. And all these are the results. And thank you so much for listening me, and I welcome you all to view my poster. Thanks you all.
Thank you. Thank you. Yes, we don't hear you.
Hello, am I audible?
The sound is very low.
Hello.
Yes, can you increase your voice?
I'm trying actually. Hello, now?
Yes, a bit better. Okay.
Okay. Hello everyone, I am Ajay Rati from Physical Research Laboratory, India. So I am working in the geoscience division here. So my topic is related to the role of micro and macro nutrients on the ocean primary productivity. So basically, ocean are responsible for half of the primary production on the Earth's surface. It is the rate at which energy is converted into organic substances by the phytoplanktons present in the surface water and form the basis of the marine food web. The rate of the primary productivity is dependent on the several factors like light, organisms, and nutrients. So in the oceans, these some of the nutrients like iron, phosphorus, and nitrogen can limit the primary productivity in the surface waters. So my objective of this study was to see the effect of this nutrient on the primary productivity. To understand the effect of these several nutrient enrichment experiment, we have performed several experiments in the northern part of the Indian Ocean, basically in the Arabian Sea and the Bay of Bengal. So this figure is showing the location of these stations. So the methodology what we have followed is like we have taken the samples from the CTD into the polycarbonate bottles and added tracers and nutrient and done the incubation for 24 hours, and then we have filtered that water and further analysis were done in the using IRMS. So after the so our hypothesis was like the primary productivity in the Bay of Bengal may be increased after the addition of nutrients, or there will be no effect in the Arabian Sea because Arabian Sea is considered as the highly productive region in the ocean. So what we have found is that primary productivity was high in after the addition of nutrient in the Arabian Sea, but we did not find any significant changes in the primary productivity in the Bay of Bengal after the addition of these nutrients. So we can say that in the Arabian Sea, the primary productivity was basically limited by the nitrogen nutrient. Thank you all.
Thank you very much.
Hello, everyone. Am I audible?
Yes.
Okay. Hello, everyone. My name is Himanshu Saxena from the Physical Research Laboratory, India. Phytoplankton assimilate carbon dioxide gas, and in a way, they help in regulating the climate of the Earth. Phytoplankton have various sources of nutrients, for example, through atmospheric deposition, through riverine input, through upwelling, through the advection of nutrient-rich waters, they get their nutrients. In addition, there are microbes called the diazotrophs are also able to fix nitrogen gas into ammonium, which is a bioavailable, or we could say bioaccessible form of nitrogen for the phytoplankton. Thereby, nitrogen fixers also help phytoplankton in assimilating the carbon dioxide and regulating the climate of the Earth. We measure nitrogen fixation and carbon fixation in a seawater using a tracer technique in which we add the tracer into a closed bottle containing the sample, and then that bottle is incubated under the presence of sunlight. And after its biomass collection of incubation, we measure the 15N or 13C content of the biomass. Then after comparing the 15N content of the particulate matter from the initial sample and the incubated sample and the amount of 15N it has acquired during fixation, we get to know the amount of nitrogen or carbon fixation that has been fixed. With this motivation, we measured the nitrogen fixation, carbon fixation rates in the Bay of Bengal, which is an oligotrophic region. And we observed that nitrogen fixation contribution to primary protection was less than 1%. Thank you.
Thank you very much.
Am I audible?
Yes.
Yeah, so greetings to all the members of SOLAS. I am Garima Shukla from CSR National Institute of Oceanography, Goa, India. So this poster reports on my research objective, which addresses the estimation of aerosol pH over a coastal location in the Eastern Arabian Sea using a thermodynamic model Isoropia 2. So this research draws on the formation of secondary inorganic aerosol and their role in the acidity of atmospheric particles. We found that the sulfate is the dominant secondary inorganic aerosol among the all, and it is playing key role in the acidity of atmospheric particles, and its dominance has resulted in high acidity in coastal region in both forward and reverse modes of the model. So the main implication of this high acidity of atmospheric aerosol influences the solubility of trace metals, enhances nutrient availability, and thus affects the biogeochemical processes in the surface oceanic water. So overall, we found that the aerosol pH majorly over the oceanic region is a promising area for further investigation with possible extension to other areas of research. Thank you.
Thank you very much. Next speaker.
Hello everyone. Hello everyone. I am Udisha from National Institute of Oceanography, Goa, India. In this study, we report geochemical composition of wet deposited particles collected at a coastal station located in the northeastern Arabian Sea during a southwest monsoon period of 2014, 15, and 19. During southwest monsoon, majority of dust reaches the eastern Arabian Sea via mid-tropospheric transport and undergoes wet deposition, which can significantly impact on surface ocean biogeochemical processes. So here in this work, an attempt is made to characterize and identify sources of mineral dust and to assess temporal variability in these sources of dust during southwest monsoon. The result based on mineralogical and isotopic composition indicates significant temporal variability in dust sources reaching to the northeastern Arabian Sea, with the major active dust sources identified as the Arabian Peninsula, Northeast Africa, Southwest Asia, and Thar Desert. In order to understand the changing pattern of dust emission from the source region, it is important to characterize dust and identify their sources, which make this study very crucial. Thank you all.
Thank you very much.
Hello everyone. I'm Vikrant Tomar from ARIS Nainital. My work includes the interaction chemistry happening over the Central Himalayas and Indo-Gangetic Plain. The Himalayas are the regions of low ozone, but the northwesterly wind from Indian subcontinent, particularly from the Indo-Gangetic Plain, which is very highly polluted, and it reaches the marine environment of the Bay of Bengal and Indian Ocean. So we did a comparative study of the tropospheric ozone in the region of Central Himalayas and Indo-Gangetic Plain. We have used UV absorption based instrument for ozone observations at the mentioned places from late autumn to early spring. So I request you to visit my poster for the outcomes and go through them. Hence, this distinctive study will allow us to study the mixing of the transported pollutants with unstained air, and also the impact and extent of the continental polluted air mass over the Indian Ocean regions. This will also help us in better estimate of the ozone budget over the oceanic region of the Bay of Bengal, Arabian Sea, and Indian Ocean. Thank you.
Thank you very much.
Hi everyone. Thank you for being here. Well, what I did until now, I'm Marcos Fontela, postdoctoral researcher of the Marine Research Center of the Universidad de Vigo in Spain. And what I did mostly was anthropogenic carbon dioxide and ocean acidification measurements from sea-based observation. What I'm going to do now, I have my first oceanographic cruise as principal investigator next September. It's called CINES, Climate Change Impact on Oceanfront's Ecosystem, the case of the Iberian upwelling system. The overall objective of the project is to identify the change and risks for marine ecosystem services deriving from the potential impact of climate change on upwelling fronts. Nothing else but my side. What happens after know was know, and see you soon. Thanks.
Thank you.
Hi everyone, can you hear me?
Yes.
Good. So my name is Anna, and I'm a PhD student at Chalmers University of Technology, and this is my poster where we have investigated the emissions from ships. So conventional fuels contain a lot of heavy metals and polyaromatic hydrocarbons. This has been restricted to some degree, but now a new technology called scrubbers are used to clean the exhaust, which means that you use seawater, you spray it over the exhaust, and then you discharge that water, and that's not regulated. So I won't go into detail, but what we see is that this water is enriched in metals, pHs, it's highly acidified and also warm. And of course, this will have an effect on the environment, marine environment, and the organisms living there. What we also see is that using this scrubber technology in different scenarios, you can actually add more, for example, chromium to the environment than you did before when you only use this heavy fuel oil. So I hope you will visit my poster, and please contact me if you have any questions regarding shipping or the marine environment, and I'm happy to answer. Thank you so much.
Thank you very much. Next one. Oh.
Hi, everyone. So I'm Benjamin from EPFL, Switzerland, and I've been working on annual aerosol chemical composition retrieved from an aerosol mass spectrometer in the Central Arctic. So mostly we're interested because the Arctic is warming faster than the rest of the world, because we have large uncertainties in aerosol cloud radiation interactions, and because there are quite a lot of changes in anthropogenic and natural sources. So we've measured aerosols during the whole year during the Mosaic campaign. And then what we aim at doing with it is to characterize the pollution from the ship emission, from local pollutions. Also understand and characterize more extreme events such as warm mass intrusions into the Arctic. And finally, we also want to understand the chemical and geographical sources of these pollutants into the Arctic. So if you have more questions, come and visit my poster and give me a comment or email me. Thanks.
Very much. Yes. We don't hear you.
Do you hear me now?
Yes.
Oh, lovely. So, hello everybody. My name is Cem. I'm a PhD candidate at the METU IMS Institute in Turkey. I work on modeling Levantine intermediate water formation in the Silesian Basin. This water mass is the main source of Mediterranean outflow into the Atlantic Ocean. So it affects the global thermohaline conveyor belt. So by extension, the global climate system. It is formed in this region that is shown on this poster. It is a thermohaline process, so LC interaction, wind-driven turbulence, as well as heat fluxes with the atmosphere plays a major role in this event. Currently, it is just a prototype, but the initial results are interesting and accurate, at least according to what data we have. So if you have any questions about modeling or input, I would love to hear from you in my poster page on HUA. So thank you.
Thank you very much. Okay, I think this is it. So it was, I really enjoyed this poster session actually. It's nice to see what, I mean, to be exposed to all the different science that all of you are doing. Now we have some time to wrap up and so if anyone have comments, questions, suggestions, this is the time before we say goodbye and meet tomorrow. Anything, I mean, any type of, anything you want to say would be useful. Lisa, do you have anything to say? You always have something to say. Something clever, I mean. Okay, so for me, it was
Sorry, I have a question.
Sure, good.
Yeah, about these ship emissions and scrubbers. So it's really unregulated. You can use this water to like wash the shit away, and then it's just emitted into the ocean. Did I get you right on that one?
Yes. So there are guidelines, but no regulations on how to much you can discharge, basically.
Okay.
Yes.
That sounds very bad.
We can continue to talk about this.
Okay.
Yes, it is. It's mind blowing.
And so if we, is it so now we have a lot of ships in the sea. The numbers are increasing, I think. Is this technology the standard now?
No, it's not a standard technology, but it's more and more ships to install it. So instead of usually ships are running on these heavy fuel oils, or they did, but then after regulations, and the regulations basically limited the amount of sulfur you were allowed to emit into the atmosphere, but it doesn't regulate how. So the aim with this regulation was to switch to more distillate fuels, like cleaner fuels, so to say. But these fuels are much more expensive, so then you need to, so as an alternative, they some ships, about 5% of the global fleet, have installed these scrubbers instead. So they continue to run on the same fuel they did before. They use the scrubbers, so the emissions to the atmosphere is compliant, but then the discharge to water is unregulated. So yeah.
So in 20 years, this will be regulated, then we have another problem. Okay.
And I think SOLAS is perfect for this because you want to have the full picture, like atmosphere, ocean, it's connected. So I think that's what's so important with all of this. I mean, everything we work on is that we see the full picture, not only atmospheric science or ocean science. We have to like put them together in a scientific way, but also in a policy way.
I agree. It's very, very compelling, very interesting. Any other comments?
Yeah. I want to have some question about that ANA poster, the SIP measurement. May I?
Yes.
Yeah. So my question is related to the ANA that they shows that that if I'm right, they have some pollutant related study on the shipborne measurements. So I just want to curious about that. They have some observation of ozone also. So how they these pollutants, primary pollutants, reflect on the secondary organic, secondary pollutants. Any comment,
So after saying that it's important to look at the atmosphere and the marine, for this study we focused on metals and polycyclic aromatic hydrocarbons. I have not looked into ozone, and I think maybe other constituents of ship emissions other than ozone is more important actually for secondary aerosol formation, but I'm not an atmospheric scientist, so I wouldn't know exactly. I'm sorry.
So have you checked with that trajectory kind of thing? Is a metallic is a in situ production or something they transport it from the other side also, because the aerosol also travel from the other side, right? Means they have the different source from the receptor side. You have SIP and in situ, but I'm saying that have you checked that these are the what it is produced by the ship or that shipborne, or they have transmitted from the other side?
So this paper and this poster is based on, I haven't done those measurements myself. It's based on other measurements. So and I've not in those studies, no one measured the in situ formation of secondary aerosols, but I know that is done like on where you have these land-based monitoring stations close to the ship lanes, for example. So data exists, but not in this poster and not in this paper. But I'm sure that there are scientists doing research on this as well.
Okay, thank you for the great work.
Thank you for your questions.
Very nice. Okay. Anyone else? I see I see mostly letters, so it's very difficult to grasp anything. So unless I'm missing something, I think we can wrap up. So it was very interesting. One comment for the lecturers, when we do the posters, they were all very, interesting and to the point. I recommend you put your name on the, at least your name on the poster. Some people didn't have it and it was difficult to do. And if you can, I know it's not possible, sometimes it's difficult and sometimes there is Wi-Fi. If you can open the camera, at least when you are talking, it is highly important. When you talk and we just hear a voice without seeing you, we miss, I don't know, 60% of your message. And one of the goals is to know each other and to see each other. It makes things much harder. So I highly recommend, if it's possible, please turn on your cameras, especially when you're talking, if it's possible, of course. This is it. We meet tomorrow. And thank you all very much.
Bye-bye. Thank you.
Bye. Thank you very
all.
much.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.